Welcome to qnawire.
In this problem, we have a parallel plate capacitor basically used to measure the level of fuel in a fuel tank. So the idea here is that you have these two parallel plates, and then they have some length here, L, and then they're partially submerged in the fuel so H, the distance H is submerged in the fuel. And so because the fuel has a different dielectric constant than the air, we can figure out, if we measure the capacitance of this total system here, we can figure out that what this fuel level would be. So what they want us to do is they want us to find the effective or total capacitance as a function of H. So H. So again, we can look at this as two parallel plate capacitors in parallel, just like we did in previous problem. And let's see here, we have if they're in parallel, then the capacitances add up. So we have the capacitance of the air gap capacitor. It's just the permittivity of free space area of the that's has air between it, divided by the distance between these two. And this is the distance between it is the same for both cases. The area is, so we'll say that we have a width W here, and that's going to drop out. So the area is L minus H times W. So we get the capacitance of this part of the capacitor is that permittivity of free space times L minus H times W divided by D. And now for the part that is submerged in the fuel, we have the dielectric constant of the fuel, the area, cross-sectional area of the plate that's submerged in the fuel, the distance, the permittivity of free space, and then the distance, which is also d. So AF is just W times H. And so now we can add if we look at the total, so we want to say the total capacitance. That's the permittivity of the total, whatever the net material is in here, which is the effective dielectric constant of the relative the permittivity of the material in here. And so now we get the area is the total area, right? And then we have the distance is the same across everything. So this is the total capacitance. And so what we want is we want to get this total, dielectric constant, or the effective dielectric constant of this total capacitor. So we know that this must equal this plus this. So putting that all together and doing some rearranging and canceling some things out, we see that W's cancel out, the D's cancel out, permittivity of free space cancels out. And so we get the effective dielectric constant of this system here is K, the dielectric constant of the fuel, minus 1, the dielectric constant of the air, times H over L plus 1. And so then they tell us that in one case we have gasoline and in one case we have methanol. And then we want to look at how this effective dielectric constant changes as the level of fuel changes. So gasoline has a dielectric constant of 1.95, which is not a whole lot. It's about twice that of what air is. So we see here that our effective are basically the slope here, which would give us the sensitivity, how sensitive this is to changes in this. So this slope is about 1 in the first case. So at when H is 0, obviously the effective dielectric constant is 1, just the same as free space. When H is L, then this is 1, then this cancels with that, and we get the effective dielectric constant is just that of the fuel, because it's completely submerged in the fuel. So we get 1 when H is 0. When H over L is, so when it's a quarter of the way up, we get 1.2 1.24. When it's half the way up, we get 1.47. When it's 3/4 of the way up, we get 1.72. And when it's all the way up, we get 1.95. So we go from 1 to 2, basically, close to 1, from about 1 to 2. And now, if we had methanol as our fuel, methanol has a very high dielectric constant, or I mean, relative to gasoline anyway. So we can see that the sensitivity here is going to be, instead of being 1, it's going to be 32. So this is going to change much more rapidly as H changes. So again, when H is 0, KT is 1. And now when H over L is 1/4, we get KT is 9. When it's a half, we get 17. And when it's 3/4, we get 25. And then when H is L, then we get, again, KT would be 33. So this would be much easier to sense if we had methanol in here, because the dielectric constant is changing a much greater amount as it goes from empty to full. And so we wouldn't have to be as sensitive to these changes, measuring these changes to figure out how much fuel is in there. With gasoline, we'd have to have much more sensitive circuitry to measure this dielectric constant, because it's not changing a whole lot. But again, we could do it. I'm not sure if this is how fuel gauges work. I would doubt it in a vehicle anyway, because this would be a pretty large parallel plates in there. But maybe, I'm not sure how in a typical automobile, how the fuel level is actually measured. There's plenty of ways of doing it, just not sure what was the most practical way, and also probably the cheapest as far as the manufacturers were concerned.